Hello and welcome. This is the next A2 physics, the astrophysics topic. Okay, this is one of the videos on that. This is the second video. Okay, so in the first video we did look at optical and non-optical telescopes. Well, in this video, what we're going to be looking at is we're going to be looking at stars. Now, that's not the stupid compliment that people give to kids. Oh, you're a star. Well, quite clearly not. You're not a hot ball of gas. It'd be quite worrying if you were a star. But anyway, yeah, that's my theory on children. Okay, so as I said, what we're going to be looking at in this video is stars. Okay, so obviously we're going to kick off just by telling the difference between brightness and luminosity and going over a few things like that. Okay, so brightness. Well, if something's bright, obviously it's more intense. Okay. Well, actually, no. I'll go on to the relationship actually between them two later. Just decided that. Okay, so brightness is defined as the amount of energy radiated. Sorry, actually, one sec. Yeah, sorry, it's better to define luminosity first. Sorry, I do apologise. So luminosity, we've got a star. If a star is very luminous, it's emitting a lot of energy per second. In other words, luminosity is the total amount of energy that is emitted per second. Sorry, I was skipping ahead of myself. Of energy that is emitted per second. In other words, you could say it is equal to the power. Okay? Now, the brightness is the total amount of energy that is emitted per second per metre squared, or in other words, brightness is equal to the luminosity, we'll define that as L, per area. In other words, the luminosity divided by the area. Okay, so essentially that's what brightness is. So luminosity is kind of if you're at the surface of the star or whatever you're measuring. Okay, but the brightness is sort of the luminosity, but you're at a certain area. We take into account the area quite clearly with brightness. So that's the key distinction between luminosity and brightness. Okay, so hopefully that's cleared a few things up. Now, what we're going to go on to do later on this video, so there's a lot of equations that we're going to be learning to do with stars. Okay, but yeah, but the first things we're going to look at is to do with apparent and absolute magnitude. Okay, personally I find this quite interesting, but maybe I'm just a little bit sad. Okay, so what the hell do we mean by apparent and absolute magnitude? Well, you can think of it as quite literal terms in terms of how it's said. Apparent magnitude is how bright it apparently seems. Okay, so in other words, we don't take into account we don't take into account certain factors. Okay, and these certain factors is just distance. Okay, so it's just how bright it seems where we are. Okay, so we don't take into account it's travelled through space and obviously time as well. We don't take into account that fact. We don't take into account the distance. Okay, so it's just how bright it appears to be. In other words, it's apparent how bright it apparently is. Okay, so it's the brightness of a star, but we don't take into account the distance. Okay, the brightness of a star, ignoring distance. Okay, and obviously this was the first magnitude to be discovered. Okay, because obviously you don't need telescopes. You can just look at the stars and you class them in terms of the magnitudes. Okay, now the first thing to get your head around with these, obviously we're given a scale for apparent magnitude, but it can be negative and it could be positive. Now, which do you think is going to have a higher magnitude? Nope, that's wrong, or could be right. What I'm trying to say is this is not what you think it's going to be. Okay, when obviously we have scales for these magnitudes, okay? And the lower the magnitude number, the brighter it is, okay? So if it's got an apparent magnitude of -7, that's a lot brighter than a magnitude of 1, okay? But let's, to give you a perspective of how the brightness varies with these magnitudes, okay, in terms of, you know, how bright it is. The star which has a magnitude of 1, okay, so a magnitude of 1 is said to be 100, so I just put mag of 1 is said to be 100 times brighter than a star with magnitude 6. Magnitude 6, okay? So a star of magnitude 1 is said to be 100 times brighter than a star of magnitude 6. So you can quite clearly say, well, therefore, obviously, a difference of 5 magnitudes is equal to 100 times the brightness, okay? And if you put that into context, okay, then you get 100 to the power of a fifth is equal to 2.5? Yeah, to 2.5. Okay, because obviously there's magnitude of 5 difference, and we multiply something each time, because obviously the magnitude's not going to be adding a magnitude, it's going to be multiplying it, okay? Because we talked about that magnitude of 1 is 100 times brighter than the magnitude of 6, okay? So really all it is about using logs to get to that. But that's the 2.5 times, okay? So you go up 1, 2.5 times. So a magnitude of 6 is 2.5 times darker or dimmer than a magnitude of 5. Okay, and obviously you repeat that process until you get to 5 jumps, okay? If that makes sense. If it doesn't, so all you need to pay attention to is that the star magnitude of 1 is 100 times brighter than the star magnitude 6, okay? So it is weird that the lower the number, the magnitude, the brighter the star is, okay? Now, the other term that I mentioned was absolute magnitude, okay? Absolute magnitude is, well, it's the brightness of a star at a set distance, okay? So absolute magnitude it's the brightness of a star at a set distance. But what is that set distance? Well, there's another way to bring about this. It's 10 parsecs or 32.6 light years. So it's the brightness of a star at that set distance. So brightness of a star at 10 light years or 32.6 parsecs. And obviously you can count that down to work out like what 1 light year is in terms of parsecs and vice versa. Okay, but as I said, that's for your own interest, and you're given that ratio in the equation sheet anyway, so don't worry about just having to remember that purely to remember the relationship between the two, okay? But that's just something you need to know about absolute magnitude. Now there are equations which I'm going to go through for both of them, but I just wanted to give you a bit of an overview of what we mean by apparent magnitude and what we mean by absolute magnitude. Okay, so I'm going to start with the easy one. And it is easier because for absolute magnitude we have to draw quite a few diagrams, well, one diagram really. But as I said, apparent magnitude, the equations are a lot simpler to understand. Okay, so just going to rub all that off. Obviously you can go back if you don't want to try and catch me, rubbing all off. Okay, so apparent magnitude, we said it's how bright the star appears to be. In other words, we don't take into account the factor of distance. Okay, so the equation, it's apparent magnitude is denoted by little m, because obviously it's not that important, so we denote it by little m. And the equation is minus 2.5 times the log of the brightness, and the log of little b. Now, you know that the brightness, obviously, is the luminosity over the area, okay? Did I mention what luminosity formula was? Or the brightness formula? No, I don't think I did. So I probably should have mentioned that. The brightness formula, that we said it's a luminosity over the area. Okay, so it's luminosity over the area, and the area obviously we generate some kind of circle, so it's 4 pi r squared, and we label it as big R because we're talking about planets and distances between planets. Okay, so that's why we label it as big R. Okay. Right. Anyway, so that's that out of the way. So obviously you could just input that into being this equation, but we're not really bothered about that. So that's the apparent magnitude of one star, star, okay? But if we're comparing two, well, we just take two of these equations away from each other to work out the difference, okay? So if we call that M1, magnitude of 1, not magnitude of 1, star 1, apparent magnitude of star 1, okay, apparent magnitude of star 2, M2, same equation, okay, obviously the brightness will be different, okay, and you just take them two equations away from each other, and now because obviously they're to do with logs, you take when you take away logs, you divide what's being logged, okay, so when you take away the equation, so M2 take M1, now good, right, M1 take M2, but I just put the second star as being brighter, okay, so obviously the first star is being brighter, I don't know, whatever which way round, it doesn't really matter, okay, because you're going to work out the brightness of 1 anyway, and it is equal to minus 2.5 times the log of, well, if we call the star 1 got a brightness of B1, and the star 2 has got a brightness of B2, okay, so, well, if we divide these two, it's B2 over B1, okay, and that is the equation that you would use. Okay, so quite clearly all it is just putting these two together and taking them away from each other, applying basic log rules that you would have learnt in C2. Okay, so very, very straightforward, just a case, as I said, of working out the difference in brightness. I mean, you could just work out the answer to M1 and M2, depending, obviously, you'd have to calculate the brightness of each star, okay, and R would be the distance you are from the planet. Okay, so the radius of the planet, sorry, because brightness, remember, you're sort of measuring what's the brightness at the surface, and the luminosity as at the area, how far away you are from the planet. Now, that might not be, you might think, oh, why is he mentioning that? Because obviously we haven't shown any equations where the luminosity and the brightness are equal to each other. But we are going to do that later on, and they look like they have the same equation, where both brightness and luminosity is sorry. Shut up before I make a mistake. We're trying to be. Oh, great! I have made a mistake. Right, I thought I had. Sorry, it's intense. Sorry, yeah. Luminosity is just how bright. It's just the equation for it. Okay. So it's the energy that it radiates per second. Sorry, I do apologise. I was thinking of... Sorry, I'll explain where I was going. Okay, so intensity is luminosity over area, and so is brightness, okay? But intensity takes into account the distance between a planet and you, whereas brightness just takes into account the brightness on the planet. So when I was mentioning before, it wasn't... I should have... mentioned intensity, not luminosity. That's very, very key. So sorry for confusing you there, even though I was probably looking at my notes as I was explaining that. I just obviously wasn't looking at them carefully enough. Anyway, so all of them equations are right. Just made a little bit of an error there, so I do apologise about that. Okay, so that's fairly simple. The equations for apparent magnitude are very, very simple, but what I'm going to do now is just going to take a little short, well, probably a second break in terms of, I'll just pause the video and draw a quick sketch on the board of, we're going to look at parallaxes, something called the parallax angle now, and we'll go on to a little bit about that. So just do a quick pause and I'll draw a diagram on the screen. Hello and welcome. This is the next little bit, okay. So what I've drawn on the board here is basically we've got the sun and the earth rotating around the sun, okay, and the distance relating to a nearby star and apparent positions of a far away star, and it just ranges from January to July. Okay, the first thing I want to go over is this. You may have done it in C2, but I just want to refresh your memory, because obviously this angle of parallax, which we'll be talking about in a minute, is measured in radians. Okay, and the conversion from degrees to radians, if you weren't sure, is angle in radians is equal to angle in degrees times by 2 pi over 360. And short explanation for that to get your head around why that is. Well, 2 pi, if you think of that, well, generally when we were looking at trig diagrams, the one that comes to mind is the CAS diagram. Okay, so 2 pi is 360, so it's like times in both sides by 1. But obviously it alters the ratio of the degrees, but it wouldn't change the radians, so you can imagine it's times both by 2 pi over 360. Okay, hopefully that makes some kind of sense, but as I said, it doesn't really matter, you just need to be able to remember that formula. Okay, so a couple of things here. You may have labelled, seen if my drawing was a little bit better, that these two lengths here, so the direct length from the Sun to the nearby star, and the nearby star to Earth in July is exactly the same, or Earth in January, but I'm focusing on this top right angle triangle here. Okay, so you think, well, that's the same distance. That can't be the case, because the hypotenuse clearly, we know way back from really early on that is the longest length, so it can't be the same length as anything else, okay? But because we're dealing with angles that are so small in this case, okay, we can assume that, and any error, any difference in the distance between, you know, this hypotenuse here and the distance between the Sun and a nearby star is so marginal that it's going to be caused mainly by errors, okay, and errors in terms of actually calculated distance from Earth in any measurement, any equipment you might be using, okay. So we just assumed it to be the same, because otherwise, if we start taking out errors, we're more likely to create another error and make our answer less correct. Okay, so anyway, next thing I want to talk about is this distance between the Earth in July and the Earth and the Sun. Okay, it's known as 1 astronomical unit. That's the mean distance, because obviously it changes and increases and decreases. But the mean distance is what we call as 1 astronomical unit. Now, don't get this confused in radioactivity when you see AU. Okay, when it is U, is a 12th of the mass of carbon. Okay, which is an astronomical, which is a totally different thing. Okay, this is an astronomical unit. That's an atomic unit, something, little u. Okay, so keep that distinction in your mind. Don't get confused. Okay, obviously, whenever you see AU in an astrophysics thing, it's going to be to do with an astronomical unit between the Earth and Sun. Okay, it's not going to be to do with anything else. Okay, but if you see AU in Unit 4, in your Unit 5, sorry, your physics exam. So actually, no, it's going to be in the same paper, isn't it? Anyway, AU with reference to astrophysics, to do with astronomical units, but radioactivity, it's to do with atomic mass. So atomic number is A, and U is the mass unit. Okay, whereas that's just an astronomical unit. Okay, so please keep that distinction in mind. All right. So to work out this parallax angle, well, what would we do? Well, it's just using basic trigonometry. We label this as R, okay, so we're going to use tan. So tan theta is equal to R over D. But because the angles are so small, sine, cos and tan are all just ratios, okay, we can say that theta is equal to R over D. And if you wanted to measure the distance between the Earth and, sorry, the Sun and the parallax star, obviously it's just a case of rearranging that. But remember, this theta is in degrees, okay, so if you want to convert it, you can do. Okay, so hopefully, as I said, that makes a little bit of sense. Some more actually info on this diagram. You can see, obviously, the Earth in July represents with the parent star position. These two stars are the same, okay, but obviously this is just it's in January and that's it in July, okay, and that's the Earth in July and Earth in January. Hopefully, so that can make sense. This nearby star, though, it doesn't rotate because it appears to be it appears to move with us. Okay, but the stars further back seem to remain fixed. Sorry, I do apologise. Just probably have to. Oh, someone's onto that. Sorry, just probably someone offering me a contract again. damn them people. Anyway, okay, so hopefully as I said that makes sense so far. But the next thing we want to talk about is angle of parallax. Well, what do we actually mean by that? And what do we? And it's going to help us to understand. What is it? Sorry, one sec. Just making sure I'm getting the wording of this right. Do excuse me. Just need to make sure I do get the wording right because it's quite crucial. Come on. Okay, yeah, so, sorry, we'll be looking at parsecs. So, we talked about parsecs, and 10 parsecs equals 10 light years is equal to 32.6 parsecs. So, therefore, obviously, 1 light year is 3.26 parsecs, okay? But what the hell is a parsec in terms of how far is it? Now, you get given it on your exam, but we need to understand where that comes from. Well, 1 parsec is also known as 1 arc second. Now, don't be put off by the fact I've just said a second there. You think time is just a distance, okay? It's the angle it's gone through, that's 1 arc second. And 1 arc second is approximately 1 over 3,600 degrees. 1 over 3,600 in degrees. Yeah, degrees, whatever. Okay, and that is what it is equal to. But obviously we want it in radians, okay? Oh, sorry, no, we don't. Yeah. Well, in radians, so you'd convert it to radians, and then what you would do is put it in this formula, okay? And the distance here, that would be 1 parsec, okay? So essentially what you do is convert this into radians, put it into this formula here, theta is equal to r over d, rearrange to get d on its own, okay, which is obviously just d is r over theta, okay, and r being 1 astronomical unit, and then you would times it, yeah, so that would give you a value for d, okay, and therefore you should get the value of d, 1 parsec, to be 3.08 times 10 to the 16 metres, I think. Just going to double check that. Yep, that's correct. So, as I said, you don't really need to be able to understand that and explain that, but it's just a nice thing to be able to do. Okay, that's the next thing. Right, okay, so that's a few more formulas for apparent magnitude, absolute magnitude that we need to know. That's to do with absolute, okay? Now, the only other equation that you need to be able to understand to do with absolute and apparent magnitude is comparing the two. Now, a little bit back in this video, I talked about the main formulas that we'd use for apparent magnitude, okay? Now, we need to compare the two, apparent and absolute, if you know 2 types of stars, okay? We're going to go on to a bit more of that if I've not mentioned it already, okay? I don't think I have. Right, so just going to rub all this out, I think. So excuse me. There we are. Okay, so just going to rub this out and then I'll give you a formula that shows you the distinction, okay, or the relationship between 2 formulas that you might will need to be aware of. Okay, I was going to say you might need to be aware of, you did, but I think you're given it in the exam anyway, so it doesn't really matter. Okay, so the formula is when you compare 2 apparent an apparent and absolute magnitude. Okay, obviously depending on whichever one is going to give you the greater answer, but it doesn't really matter. The formula is little m take big M, so apparent take absolute magnitude is equal to minus 2.5 times the log of 10 over d all squared. Okay, so that's the formula. But if you want to work out what d is, I'll just show you the rearrangement now. Okay, the first thing we would do is alter this so that we get this step. Okay, so we still got m take m on the left hand side, and that is equal to 5. So we bring the 2 to the front, but instead of being minus 5, because we're flipping this, if you can imagine, we're taking the negative of this 2.5, because essentially it's minus 2.5 log d, 10 over d, if you ignore the square bit, okay, it's essentially 2.5 log d, 10 take 2.5 log d, but we take the negative, so we flip it around, okay, Hopefully that makes sense. So it's 5 log d over 10. And obviously we brought out the squared. And then you would split this 5 log d over 10 into more simple terms. Okay, so little m take big M is equal to 5 log of d take 5 log 10. And if you put 5 log 10 into your calculator, because we're assuming these logs to be base 10 when we don't write anything, obviously if we write 10 as well. Anyway, okay, so basically what that comes to is little m take big M is equal to 5 log d. That doesn't change because we don't know what d is. But 5 log 10 just comes to 5 minus 5, okay? So you rearrange this to get 5 log d as the subject because we want d to be the subject, okay? So it's 5 log d is equal to little m take big M plus 5, okay? And then you divide both sides by 5, okay? So you should get log d is equal to little m take big M plus 5 all over 5, okay? And then obviously we've got log d is equal to that. Now because this is a log base 10 and using our log rules of log b in base a is equal to n, so therefore a to the power n is equal to b, okay? So that log rule there, we just applied that log rule to this case to work out d. Obviously d being in that case the b, sorry. So therefore d, using that formula there, is equal to 10, because that's your a, to the power n, okay, which is, so it's d is equal to 10 to the power of m take big M plus 5 all over 5. Okay, and that would be your rearranged formula for working out the distance. Okay, now any equation where we have d in terms of logs, the distance is not given in meters. It is in fact, sorry, let me just double check before I waffle on. Is in fact given in parsecs, okay? Yeah, okay. So that distance, what if you were to put numbers of apparent magnitudes into that equation, you would be given it in parsecs. It's crucial to be able to work that out, obviously, because we haven't got units for little m and big M, so therefore we can't just do what we do in AS and work it out from timesing the units together or dividing them where necessary, okay? So you need to know that any distance equation relating, obviously this one's the main one, is given in parsecs, because the only other log one is to do with brightness, and obviously that's given as watts, okay? So hopefully that makes sense. And obviously you might want to manipulate that equation with the other equation, say k. So little m, apparent magnitude, is equal to minus 2.5 log of the brightness, okay? And you might manipulate that equation, so they put little m into the little m in that equation, and you might have to do a bit of substitution, okay? But that's just basic algebra skills, really. This is just rearranging, and you could just do that by working out, you know, putting in your numbers and subbing it out. So you could do that. You'd have to remember that rearrangement, but it's always nice too, okay? So just so you can come up with it on the day. As you can see, it's fairly self-explanatory, and I think I might not have got this bit, okay? I might just expanded that and then divided it, and you would have ended up with a slightly different equation, okay? So hopefully it's not too challenging. Okay, so that's the end of classifying stars by brightness, magnitude. We can't do anything else with that. The next stage is we're going to be looking at classifying stars by their temperature. Okay, so the first thing, obviously, that I need to do is rub all of it out again. I'm going to start by looking at Stephan's law, but before we do, actually, yeah, I'll state Stephan's law, and then I'll just explain a little bit about it. Okay, so Stephan's law said the power emitted by a star, in other words the energy radiated per second, is equal to this rho, which is known as Boltzmann's constant, times the area times the temperature to the power 4. Okay. I think that Boltzmann constant is given in your formula sheet. I think it's 5.67 times 10 to the minus 8 watts per meter squared per Kelvin to the power of minus 4. Okay. So that's something called Stefan's law. Okay. So obviously it takes into account the area. Now that's the surface area, what you're considering. Okay. And the temperature is obviously given in Kelvin as well. Obviously, therefore the power is given. You can just, as we did in AS, multiply out the units together to give you a complete answer. Okay, but going back to the idea when we were talking about luminosity at the start of this video, we said luminosity is the energy radiated per second. Okay. So it's the energy rated. Energy emitted per second, sorry. So therefore, with this power equation that we've got on the board, we can simply just put in because the luminosity is equal to the power output, and this is the power output equation, we can just put the luminosity equal to that. And it means exactly the same thing, okay? If you get asked to calculate the luminosity, you should know it's the same as power, so we can use this Stefan's law equation, okay? Now if we wanted to work out the intensity of that, okay, well the intensity is power over area, so you would just cancel out the areas and intensity be Boltzmann constant times temperature to the power 4. Now I think I mentioned this distinction between brightness and intensity. Now they both state in their equations, so both of these equations, I think they're given in your formula sheet, that brightness is equal to the luminosity over the area, but the intensity is also given as the luminosity over the area. But the brightness, this area, this cross-sectional area, is just the area, surface area of the planet, okay? But the intensity takes into account the area of this whole circle that you're far away from the planet from, okay? So that area there, okay? And that's the area of the intensity, okay? So there's a key distinction between them two. I think, as I said, I think I mentioned it before, but if I didn't, that's essentially what I mean. Okay, and obviously you can work out the areas, you can manipulate them to equations for luminosity and power, okay, by just subbing in that the area is 4 pi r squared or whatever you might be looking at, okay. Right, so that's the distinction between power and luminosity. Okay, now you might get asked in equations where this is the power of one star, this is the power of another, okay, and be asked to compare them where you would just come up with the power equation for one star and the power equation for the other star. They would look the same, okay, but it might be different in terms of, it might ask you to manipulate the equation using just rearrangement, okay. But as I said, hopefully it doesn't make, it's not too bad. Okay, so this T, by the way, is the surface temperature of that planet, and quite clearly, as I said, it's given in Kelvin, okay, and the area was obviously just the surface area of the star, okay. So hopefully, as I said, that makes a little bit more sense. If there's anything more on there actually. No, that's it. Okay, so this next little bit, so obviously you would be asked to use that and given equations, okay, that we know already with brightness and power for luminosity, said manipulated equations, and all the equations are given in your formula sheet, so it's just a case in them type of questions where you might get asked, this is a power of one star, what's the luminosity, or what's the surface area, or what's the temperature, you know, might be say, you know, one star's got the 3 times the power of another star, and you just manipulate that in that way. So it's basically just rearranging equations is one of the questions that you might get asked. But hopefully you're good enough at algebra. I don't need to go through that. Just remember that temperature is to the power of 4. I know it's a stupid mistake, but sometimes it's quite easily, because you most commonly use powers as squares, but just remember that temperature is always the power of 4 and it's in Kelvin, okay? So if it tells you the temperature in degrees, okay, you just have to add 237.5, I think, that's the right example. You have to add the difference between them. Anyway, pretty sure that's it. You can just have a double check and make sure I'm right online. Okay, so the next thing we're going to talk about is black bodies and black body radiation. Okay, so what the hell is a black body? Without being stereotypically racist, a black body is just an astronomical object, so a planet, a rock, whatever. Okay, so a black body is an astronomical object in which the radiation entering, so it absorbs the same radiation it emits. In other words, any radiation emitted is absorbed is emitted straight back. Okay, so it's any astronomical object in which any radiation absorbed is emitted. Okay, so that's what a black body is. Now, if you was to work out, because obviously in radiation we have to do with photons, which you can come up with have a certain wavelength, because obviously you define photons as E equals HF, and you can work out the wavelength of such radiation. Okay, so you could detect whether it is a black body or not. You might get curves where you have power radiated against wavelength for a particular black body. Okay, so in other words, power against wavelength. So power against wavelength, you might get something like that for a black body. Sorry, I really can't draw a curve anymore. Just a straight down curve. Okay, so that might be a power against wavelength curve for a black body, for example. Okay. But this peak wavelength up here, how would we calculate it? This is the thing that is come up by Wiens even displacement law, okay, which says the maximum wavelength, okay, times the temperature is always equal to a constant, where this constant is 0.0029 mK. Now mK is not millikelvin, it's meter Kelvin, and that's because, well, as I said, working out the way you work out units in AS, okay, obviously lambda is measured in meters and temperature is measured in Kelvin, so you times them two together, so therefore you get mK, which is quite clearly meter Kelvin, not millikelvin, and that's the reason behind that. Okay, so that's something called Wiens displacement law, which, as I said, would just be a case of you inputting that, rearranging it and subbing it into any other equations that we come to look at in the future. Okay, but in the exam you don't need to remember the constant or the equation, you are given both. Okay, which is quite nice. I think you're actually given the constant actually in the formula on the formula sheet, so you didn't even have to remember that constant of 0.029 goes with lambda t. Okay, even tells you, which is really quite nice. All right. There's a graph here. Yep. Okay. So I'm just going to have a stab at drawing this graph. So should I pause the video? Yeah, I'll pause the video because I want to do this quite well. Okay. Okay, so welcome back. I've just drawn this graph on the board here, obviously, and all it is showing intensity against wavelength. Okay. Now, obviously, the higher line, the blue, is representing a hot star. Okay, this is radiation. It's intensity. So, as we know, the intensity equation is luminosity over area. Okay. Same as brightness, but we're talking about the distance from a planet, not the surface. Okay, so keep your mind about that in intensity. And really, all this shows is a lower wavelengths, we've got a higher intensity for each star. Okay, but obviously the peak, this is meant to be more. The peak of the 6,000 is meant to be more over to the right than the 12,000, but it's just the way I've drawn it. It doesn't quite look like that. So basically, the peaks kind of more to the right as you get cooler, okay, and quite clearly they get lower as well, as you can see. So you might use this graph, okay, so if we're using Wiens' displacement law of lambda t is equal to a constant of 0.0029 mk, okay, remember that's meter Kelvin, you might know the intensity and you go, okay, well what is the temperature at that intensity? So you'd obviously do a line across to whatever star you were talking about, go down, read off the wavelength, okay? If this was the case, you would be given this graph, you need to remember it obviously. And then obviously, that would give you a wavelength of whatever that is, and you just sub that wavelength, okay, into that equation, and then it's just a case of rearranging it to get your either temperature, and if it asks for in degrees, then obviously you need to convert it, because that would give it you in Kelvin, okay? So, just a thing to remember there. Okay, so a very, very simple diagram there. And you might just get asked to use that lambda t equation with other equations, okay? So I think I mentioned that before anyway when I was talking about Wiens' displacement law. We're just mixing it with the power equation, which is of course P is equal to the Boltzmann constant area times the temperature to the power of 4 in Kelvin, okay? Now, what we're going to look at now is differences between emission spectrum, the continuous spectrum, and something called the absorption spectrum. And really, it might be a good idea at this point, because I mean, I'm going to try and attempt, I say attempt quite clearly because it's not probably going to go that well, to kind of draw the comparisons between a continuous, a continuous absorption and emission spectrum, forgetting the word, so continuous absorption and emission spectrum on here, and I'll do a little bit of a diagram in terms of how it goes through it so you can imagine it, but I'm sure there are diagrams of this comparing the three and the spectrums that you would see, okay? So let's start with the first one, the emission spectrum. Now this hopefully should be fairly obvious, okay? Because obviously, if you did tertiary physics, which I'm assuming you did to get to this stage, unless you've just skipped a few years, emission spectrum is to do with when I was mentioning in quantum phenomena about characteristic frequencies. Okay, so this is when you know an atom is excited. An electron is excited within the atom to a higher state, and it produces a photon with exactly the same energy that it is going to move up state. But because obviously we know E equals hf, h is a constant, so therefore the energy of this photon depends on its frequency. Okay, that's what gives it characteristic frequencies and therefore characteristic wavelengths. Because obviously we know there's many equations that link wavelength and frequency. The main one being c equals f lambda. Okay. All right, so that's essentially what a guide to an emission spectrum is. It's something you can be doing in the lab, and it's very, very simple. Okay, I'm just going to have a go now at drawing this spectrum. Okay, so as I said, obviously it's different for whatever you are testing. Okay, but if we assume to be testing, I don't know, hydrogen. Okay, so there'd be 6 lines, obviously, and that's because that's a different path the electron can take to go from 3 to 2, 2 to 1, 1 to 0, or 2 to 1, and then 2 to 0, 1 to 0, or 3 to 0. Okay, so obviously there's going to be 6 different types there. So obviously you get 6 different photons from hydrogen. Or, I don't know, whichever one. It's not the best, is it? Okay, so essentially what we should get is 6 lines, and as I said, they might not be specifically like this. Okay, so that's why I say look in line, because what these lines are meant to represent is the colour, the shade they didn't get even, so in just case the line, that is where the photons that's the wavelength, okay, because obviously it goes across in terms of wavelength, okay. And essentially, what we do for that is we put it through. It goes through a hot gas. Okay, so obviously we heat it up to give it this energy. Okay, so that is something we call the emission spectrum, which, as I said, may be sort of familiar to you from last year. But these next two, okay, may be a little bit more different. Okay, so the next thing that we can talk about, I personally would like to talk about, is the absorption spectrum. Now the absorption spectrum is essentially almost the opposite of this emission spectrum, and I'll explain why. Okay, so in the emission spectrum, what happened was the photons, obviously the electrons, were excited, and then they dropped back down to their original state, and then released the energy in the form of a photon, which gave these characteristic frequencies. Now, what happens in the absorption spectrum is that this light or energy or whatever it is passed through. Well, obviously it's light. Is passed through a cold gas. Okay, so it's the same principle. We put the photons through this cold gas, and obviously the cold gas, because it takes in energy. Okay, so it's cold, so it wants to heat up, so it takes in energy. Okay, so therefore what happens is it's kind of the opposite effect. These photons therefore don't reach the spectrum lines. Okay, so what we get is the opposite end of the scale. So where we have these single lines, okay, in the emission spectrum, there is now a gap in the absorption spectrum. But where we didn't have anything, it was just blank spacing behind it. In the absorption spectrum, it's now shaded. So I'll try and do said. So obviously the absorption spectrum is a lot greater. So I do apologise, but you get the idea. All of that is in not coloured. Okay, so try and split it up so you can see where we're going with this. So I do apologise, but hopefully you can see from my kind of crap drawing that where there is lines, okay. Okay, so that is what we call an absorption spectrum. So it might be a better idea, because obviously I could do colours, but you get the idea. And as I say, you can always look online, and there's fairly good examples online anyway. Okay, right. Okay, so that's the two. Now the next one that we want to talk about. So just put a note next to the absorption spectrum that the photons are passed through a cold gas which absorbs them, and that's why we get these gaps. Okay, photons are passed through cold gas. The next one we're going to look at is something called the continuous spectrum, which is, yes, you guessed, it's continuous. So what essentially happens here? Well, it's a large scale of the emission spectrum. Okay, and basically the way to think of this is the continuous spectrum is where there's lines all across. So in other words, it's the emission spectrum plus the absorption spectrum. So in other words, we get a bar which is completely full. And obviously, if you look online, there's the colours that match. There'll be certain colours. Okay, and basically it will be the emission spectrum and the absorption spectrum. The colours sort of added together where the gaps are. Okay, and you get this continuous spectrum. And how the hell does that happen? Well, because the same principle applies. This is just on a larger scale. So why is it so much different? Well, this continuous spectrum is likely something you to see in the sun. Okay, and what essentially happens is the same principle happens in the emission spectrum, where electrons inside the atoms are excited. But they're excited because there's so many of them on such a large scale. When one bounces up just before it selects its level, it gets boosted up another level. So you can think of it as it's almost like it's releasing two photons. Okay, because it's releasing a photon from its energy level to where it should be if it hadn't been excited twice. Okay, and then a photon from that wavelength. So in other words, this is the way to think of it. Okay, so if we've got on the very first energy level, naturally, if it just got bumped up once, it would get the energy to go to the first layer, out to the first shell, but then it would go to the second shell because it gets bumped up again because it gets bumped by another photon, okay, incoming photon from some other collision that has occurred in this massive experiment, okay? And what happens is obviously there's a photon here and a photon there, and then a photon which is combining the two. So essentially there's three photons. And what happens is you can see it already looks like a mess. But they overlap each other. In other words, they blur the lines, okay? So it's essentially these two put together. But because they're put together, you can't see the distinction, which is why we get this continuous spectrum. So hopefully that's kind of explained that, okay? So the continuous spectrum is just something you would see in the sun, for example, okay? It's just pure light going straight through. Okay. Now all of these lights have been passed through a prism, okay, to split it up. They don't just exist and we don't pull some lines out of thin air, okay. So all of these, even you know, the ones that are excited, after the light goes through whatever it's going through, in case in the first of the emission spectrum, it would go through, it would go through the hot gas, and then it would go through the prism. Whereas the absorption spectrum goes through the hot gas, then it goes through the cold gas. Well, it goes through the cold gas, sorry, and then the continuous spectrum just goes through the prism. Okay, so as I said, there'll be trying to find the words there. There'll be a good picture, as I said. There will be a good picture online. Okay, so hopefully that makes some kind of sense. Now, again, another diagram I'll have to draw. So I do apologise for all this pausing, but you can see why I am. Otherwise, you'd spend most of the video looking at the back of my head, which I'm assuming you probably don't want to do. So I'll just pause the video and just have a go at drawing this. Okay. So I've drawn two diagrams on the board. Now I do apologise for my rather crap drawings, but so you can get the pictures online. Okay, so on the left here what we have is we have the intensity of the absorption line. In other words, the intensity of the radiation given off by each of these. Okay, so each of these, now they're different elements, okay, and the heavier elements are situated in hotter stars, okay. And as you can see, as we get cooler, because the temperature decreases as you get towards the right hand side of the graph on the left, there are a lot more elements in cooler stars than there are lighter stars. Than there are hotter stars even, sorry. Okay, so as I said, hopefully you can see where all these are coming from. And these are just different intensities, okay, of the components, the atoms, elements even, which make up these stars, okay. And what I've done is I've categorised them into special, spectral classes, okay? So these are spectral classes which show, see in the O class, we've got a lot higher, more denser elements which are burn brighter, give a higher temperature, okay? And then the elements which are in the lower spectral classes, there are many more of them, but they burn at lower temperatures. Okay, so really what we're showing here is just it's a different the spectral classes, and you need to remember the order. Now I just simply, because I'm a bit weird, OBAFG, okay, which is OBAFGKM, or you could almost name it as it's almost like Obama, but they put the M at the end and put FGK in the middle. Now, as I said, either one works. If you've got any special little acronyms, you're more than welcome to state them in the comments below so other people can remember that as well. But really, I just remember it because it sounds funny. So, yeah. Okay, so anyway, that's just the graph there showing the intensity against the temperature. This is the graph that you're more likely that we can talk more about, and probably more likely to be asked on as well. There's this Hertzsprung diagram. Now, you can see here at the bottom, if you can quite make it out, but I put like a little line here, and in each one of these there's the spectral classes O, B, A, F, G, K or M, okay, and obviously this on the bottom is surface temperature, and obviously that corresponds with the temperatures that would be here if I'd have drawn it correctly, okay, and obviously they're all different spectral classes, okay, and it shows us, basically, it shows us all the different stages of the life cycle of a star, okay, and it shows us, obviously, the size, obviously, because we can look at the size over here of the elements, we can tell what it's made up of by comparing these two diagrams, okay, that's kind of why I put them together. And we also tell the stage of its cycle, life cycle, because obviously the absolute magnitude as well gives us an indication of how bright it is. So the stars at the top, even though it's a minus, they're a lot brighter, okay, whereas the stars at the bottom are very, very dim. So you can just work out, obviously, at the top right, there's the maximum magnitude and minimum temperature, okay, so over here, the supergiants and the giants, we've got a very high, we've got a very high brightness or magnitude and absolute magnitude, but we've got a very, very low temperature. Well, say 2,500, that's quite low. That's something we call TOSI. Okay, so, as I said, you can just make it up from the diagram. It's quite clear what path a normal would take. Okay, so it's obviously depending on whether it becomes a super. If it just becomes a giant, then it's just going to do that. Okay, go this and then go that way. Hopefully, that makes some kind of sense. Now, not really too many theories or such as you need to know about that. Okay, but it's just showing you the comparison between this diagram and the Hertzsprung diagram. Okay. And, you know, it does show us quite a lot, such as temperature, size, magnitude, brightness. Just a few things you need to be able to spot from this diagram, really. And it's quite clear that at the bottom left, we've got the lowest absolute magnitude with the highest temperature. So the white dwarfs are very, very dim, but they are very, very hot. Okay, whereas at the top left, we've got the very, very high absolute magnitude, which is, even though it's negative, we class it as very, very bright. And the highest of the surface temperatures. Okay, so towards kind of this end of the main sequence, okay, obviously different stars would stop the main sequence at different points, but this is just kind of a collective diagram of quite a few stars, okay, and obviously some comes from supergiants and some don't, and some just become don't become stars. Now what we're going to look at now is the actual order of this, and what I'm going to do now, you don't need to necessarily know every single bit of what I'm about to say because it's not in the specification, but there's no harm in doing a bit more at the end of the day. All you really need to know is kind of the sequence of what happens to certain stars and kind of what a few of the things that, you know, what the nuclear fusion is and stuff. So kind of all you really need to know is kind of GCSE level kind of stuff for this. But I'd like to go a little bit further on. Okay, so what I've done here is I've broken down the life cycle of a star according to its size. Now, GCSE might say, a very big star or a star the size of our sun. Now that is a very, very childish explanation, if you can call it childish. What we do at A2 to make ourselves seem like we've progressed in life is come up with this thing, well, not come up with it, it's existing, just like, do it out of the ground, called a solar mass. And now that is what is relative to the size of our sun. So quite clearly, an astronomical object, planet, star, which has got a solar mass of 1, is the same size as our sun, or obviously if it's got a solar mass of 2, it's twice as big as our sun, and etc, etc. Okay, so what I'm going to do is break down different life cycles of stars according to their solar mass. So whenever you hear me say solar mass, it's relative to our sun, okay? So the first type we're going to talk about is anything less that's got a solar mass which is less than 0.1 solar masses. SM for short, obviously. Okay, anything that's got a solar mass less than 0.1 is not going to become a star. It's just going to be a very, very cold, black, brown ball of dust, okay? It's not going to get enough energy because it's not big enough. It's not going to draw. It's not, you know, because we were talking about that gravitational attraction is the attraction between big objects and small objects, okay? Well, anything less than 0.1 solar mass, well, it's still fairly big. You know, even if it is getting close to 0.1 solar masses, but it's not big enough to start the life cycle of a star. So it will almost make it, okay? Obviously, depending how close it is. But really, what happens, it just remains the small what's the wording? Brown sort of cloud of dust, really. And obviously, there's no real you know, reactions or anything you need to know about with that dust. Okay, so the next type of star we're going to look at is anything that's got a you know, a solar mass of between. Anything that's got a solar mass of between, say 0.1, bigger than 0.1 clearly, and between 0.1 and 1.4 solar masses. Okay, so these start off with what we call a protostar, which is what the 0.1 solar mass was going to turn into, but obviously it failed because it wasn't big enough. Okay, so what we have here is something called a protostar, which is just, it's a collection of bits of matter and gas and dust, really. It's just where it starts to spin around, because obviously the bigger chunks of, the more dense gas and the rocks and that kind of thing, they group together because they're attracted to each other because it's bigger. You know, just like girls, well, girls, boys even, people are attracted to people with bigger wallets than they have, okay, so they can divorce them and get the money. Okay, but anyway, same principle happens with attraction with bigger objects. Anyway, so this protostar kind of spins round, you know, all the gas, it begins to spin around and generate quite a bit of heat. And it generates enough heat to start nuclear fusion, which the 0.1 solar mass, or the less than that, didn't do. Okay, that's why it didn't become a star, because it wasn't spinning fast enough to generate friction between the molecules, the gases, to generate nuclear fusion. Now you should know, I did a video on nuclear fusion and nuclear fission. Fusion is essentially firing neutrons at an unstable nucleus, okay, and basically fusing them together, making the nucleus bigger, okay. So anyway, that's what nuclear fusion is. As I said, there's a video on that, so please do check it out if you're not sure about that. Anyway, so this protostar is just a collection of ball and gas that starts to spin around and generate a bit of nuclear fusion. And when it does, when it starts generating nuclear fusion, we call that now as the main sequence, is what our sun is in. Okay. Now, obviously, you need to know a bit more than you did about GCSE about this. Okay, so the main sequence, now obviously you know that's the longest period. It's approximately about 10 billion years, so long enough, you know, when people say, oh, the world's going to end, you know, we're going to be sucked into a giant black hole by the sun. Well, very true, but we're quite clearly going to not be around for that, so I'm not bothered. Let somebody else deal with it. Anyway, so in this, we said that nuclear fusion happens. And what happens at this stage of nuclear fusion is the hydrogen is fusing to become helium. So hydrogen is fusing with helium. So hydrogen is fusing to helium. And that's essentially what happens in the main sequence. And as we know, the nuclear fusion is pushing out, trying to push out, and obviously because it's getting bigger, it's attracted more things into the centre, so therefore there's a counteracting force of the gravitational attraction. But then after that, what happens is obviously the nuclear fusion begins to be used up, and the rate of nuclear fusion slows down. Okay, and what we get is, just as that begins to happen, the rate of nuclear fusion begins to slow down, we get something called the red giant. Okay, now it does become a supergiant, but we'll talk about that. Well, it doesn't become a supergiant, red supergiant in this range. It's in the next range that happens. But I'll go on to compare the two life cycles in a minute. Okay, but anyway, so the main sequence, when the rate of nuclear fusion starts to slow down, when the hydrogen begins to be used up, okay, when that rate starts to slow down, it becomes a red giant, okay? And when the hydrogen has been all used up, the helium starts fusing with carbon and oxygen, okay? So that's what happens when the helium runs out. And obviously, when that begins to happen, there's a lot, obviously, the force pushing out is a lot less than the force pushing in. Okay, so obviously what happens is it shrinks and it folds in on itself. And essentially what happens is, obviously, all of this force is kind of stopping the nuclear fusion taking place. Okay. And when it becomes, it condenses, all this gravitational force pushes it together, and it becomes a very dense, small star, okay? And what it becomes is something we call a planetary nebula. Okay? And then once this happens, okay, so when it becomes a planetary nebula, that's just what we say when it's all condensed and it stops shrinking. But then after it stops shrinking, any remaining, helium with the carbon and oxygen which hasn't fused begins to fuse again, because obviously it's not shrinking anymore, so therefore it's able to start going again. Okay, and what happens then is we have something called a white dwarf, which is what we saw in Hertzsprung. I've been calling it the wrong thing, have I? Sec. Hertzsprung-Russell, yeah, I'm going to snap the name. Sorry, Russell. Hertzsprung-Russell diagram, okay, we showed that the white dwarf is very hot, and this is because the nuclear fusion has already taken place, but it's continuing to take place again, so the temperature is increasing, okay? So the white dwarf is essentially where we have some more helium fusing with carbon and oxygen, okay? So that's what's happening in the white dwarf stage, okay? So then after the white dwarf stage, what happens is, obviously, when all of it's completely run out, and all the gas has been burnt up, okay, we end up with something called a black dwarf, which has never been seen because it takes such a long period of time. I mean, you think, by the main sequence, already 10 billion years has passed, and I think the world's only a few billion years older than that. So really, you know, all these stages aren't going to happen in a few years, alright? So it's very unlikely that you would see a black dwarf. And I think it's said that about 90% of the stars that we see in the sky are in their main sequence, okay? So it's very, very nice, and we're never going to see the end of that for them stars. And obviously, unless science invents a life where we can all live forever, and I reckon the government's probably already thought of that, you know, kind of a Matrix theme where, you know, if it makes sense for them to hide it if they did have it, so they probably have worked out a way to make us live forever. So I'm going to try and work it out for you, and I'll put it out there so we can all live forever. But before that, we need to carry on with this astrophysics stuff, working out more about the universe, and then work out how we can live forever. Okay, so that's the stars that are between 0.1 and 1.4 solar mass. But what happens when we increase the solar mass of a particular planet, and the solar mass is now greater than 1.4? Okay, well obviously, well it's obvious, it starts in exactly the same way, okay, so it begins with a protostar just like the previous stage, the previous star, okay, so it becomes a protostar in exactly the same way, but from just about towards the main difference, okay, up to the end of the main sequence star, they are exactly the same. Alright, so they both have a main sequence of about 10 billion years. But because obviously there's a much greater solar mass with a star that's greater than 1.4, that means there's a lot more hydrogen to fuse with the helium, okay? So the same nuclear fusion still takes place with the hydrogen turning into helium, okay? Obviously, when that slows down, we get, we don't, because that's increasing at such a large rate, okay, because it's similar time periods, it's still about 10 billion years, okay, and what happens then is, they still, you know, it still folds in on itself, but because it's been much bigger, because of its forces are pushing it out much more, that's obviously why it's called a red supergiant, or just supergiant, I label them as red supergiants, why not, okay, so red supergiants. Now, because they're a lot bigger, with the name supergiants, obviously the force that is now pushing them in, gravitational, is a lot stronger. But they've still run out of the nuclear fusion that takes place. The hydrogens have still all been fused with helium. So there's still the same amount of pushing out force, i.e. none, okay? But because the gravitational force of the mass actually being a hell of a lot bigger, therefore the difference between the two, obviously, if one's bigger and the other is the same, then obviously the resultant is going to be a lot greater, okay? So there's a lot greater force pushing it together, okay? So in other words, what happens is it rapidly shrinks, okay? And in other words, what happens here is something called a supernova, okay? It's a supernova explosion. A very, very large explosion, which in some cases can actually outshine the rest of the universe. I do that every day, but you know, that's just my opinion. Okay, so supernova, and they can produce up to 10 to the power of 46 joules, which is what my grandma would say is quite a lot. What I would say quite a lot as well. Anyway, so supernova is about 10 to the 46 joules. Okay, so it's very, very bright. And from there, what happens next is wholly dependent on, again, the mass, solar mass. So again, we've got to do this thing of splitting it up into a further two diagrams here, okay? So what we've got, okay, is it depends obviously on the solar mass. Now, if the solar mass is greater than 3, okay, the two stories, you can look at it like this, is if it's greater than 3 solar masses, or if it's less than 3 solar masses. Okay, and if it's less than 3 solar masses, it essentially what it does is just contracts into something called a neutron star. Now, a neutron star is well, hints in the name, it's a neutron star. So it's the same size as a neutron, and it's essentially covered with a very thin. Inside's very, there's a lot of neutrons. Okay, but it's about a neutron thick, and it's covered in an iron crusty core. Okay, so it's very, very hard to escape from. Because of this, there's a lot of the charges that are to deal with. Okay, and if you want to escape, you'll be approaching 0.8 times 10. Sorry, not 0.8, not 0.8 times the speed of light. Okay, so that's very, very fast, almost unescapable. Okay, in terms of if you're at speed of light. Okay, so obviously anything greater than 3 solar masses is going to have a slightly different effect. It's going to have a lot bigger. We're going to go into something in a minute, actually. Yeah. So anyway, there's 3 solar masses is a lot bigger, and what happens is because it's a lot bigger, the forces are also a lot bigger, and so this 3 solar masses, it hasn't just jumped to 3 solar masses. This just says the start, this protostar, this third idea. It just says it's greater than 1.4. It doesn't say if it's bigger than 3 or less than 3. Obviously, this less than 3 is when it's greater than 1.4, because to be on this third stage, to start this third stage, it needs to have a solar mass which is greater than 1.4. Now, we didn't say explicitly, it's 2.8 or 19.6. Now we can classify it further. This is the 3, the bigger than 3 solar mass. Okay, so if it's bigger than 3 solar masses, the forces are a lot greater. This explosion is a lot greater. So this 10 to the 46 joules is more likely to be associated with an explosion which has been greater than 3 solar masses. Okay, so if it's greater than 3 solar masses, then what happens is it creates a black hole. Okay, and this black hole is, nothing can escape it up to a certain boundary. Okay, so nothing can escape this black hole up to a certain boundary. Okay, and that's because not even light can escape. Light's not fast enough to escape. Okay, so you're Mark Wahlberg from that Martian program, or this film, or whatever it was. He'd be dead. He would be dead. I mean, I'm sure the American film industry, British film industry, whatever it is, would find a way to make him survive a black hole. Well, if he was sucked into a black hole, he'd be quite dead. Pretty dead. Dead. Anyway, so a black hole. Now, I said up to a boundary. I'm just that boundary is something we call the Schwarzschild radius, and I'm just going to do a few formulas on that. So, for the moment, what I'm going to do is, I'll pause the video, and what I'm going to do is rub all the top half of this off, okay, and I'm going to redraw this bottom half, okay, so this 1.4 solar masses, that is greater than 1.4, I'm going to draw that back at the top, and then I'm going to explain the equations that are to do with the Schwarzschild radius. So if you want to get ahead and note that down before I rub it off, obviously, just hit the old pause button, and we'll see you in the next little bit of the video. Okay, so welcome back. This is essentially what I've drawn, essentially what was in the last little paragraph, but I've just kind of emphasised it, kind of made it obviously bigger. Excuse me, it's classy. Okay, so, and I've just wrote in blue what I mentioned at the end, but I didn't write down on the board. Okay, there's a couple of things that I want to go over these two to finish off, and depending on how long's left on my camera in terms of the recording space, and depending on what I decide to do, I might in this video introduce black holes, but obviously that will be in the title of the video if I do. Okay, so this neutron star, the thing that I want to go over with this, well, it says it needs, I said that we need an escape velocity of approximately approaching 0.8 times the speed of light. But how do we actually calculate that? Well, we use the idea of gravitational velocity, okay? So in the video, in the gravitational video fields, I gave a formula that was something like this. The velocity is the square root of 2gm over r. Now granted, the velocity equation that I gave you in gravitational fields was slightly different, but we are dealing with a slightly different aspect here. So as I said, that velocity equation is given to you in the exam. Now black holes, I'm going to come up with this r, okay, this Schwarzschild radius, sorry. Now, in terms of velocity, okay, we were talking about no light can escape the centre. Say, so obviously the first speed of anything that's going to be able to escape this black hole at the minimum point is going to be speed of light. Okay, so obviously the velocity is going to be the speed of light. By that way, that's the escape velocity for a neutron star. So using the same equation that we've done for the neutron star, but instead of putting velocity, escape velocity, we know that's equal to the speed of light because that's the first thing that's going to be able to escape this black hole. Okay, we put that as c. Okay, and that's equal to the square root of 2gm over, I'm going to put r and then subscript this Schwarzschild radius, or you can just leave it as r. Okay, Schwarzschild radius. And it's just a case of rearranging this to get the r. Okay, so r is obviously there for, sorry, is it? Over all the square, sorry, one sec, let me double check that. Do apologise. Sorry, it's the square root of all of it, I do apologise. So it's the square root, the escape velocity is equal to the square root of 2gm over r, it's not just the square of 2gm. So that's more like the actual equation that we were given in the exam. Sorry, in the gravitational fields. Anyway, so if you were to, therefore, if you were to rearrange that equation, you obviously square both sides and then rearrange to get r. So then obviously the r would be 2gm over the speed of light squared. And that's the Schwarzschild radius for a black hole. Obviously you would have to input your values there, the mass of the black hole. Now, obviously, you could say that the, you could obviously G there is obviously the gravitational constant, which is the same as it was, obviously weirdly enough, in gravitational fields of 6.67 times 10 to the minus 11, I think it was, approximately. Okay, and so obviously newtons and stuff as units. Alright. Okay, so hopefully, as I said, that made some kind of sense. Let me just double check how long I've got left on this video. Yeah, why not? I'm sure I'll have a go at fitting it in. So I'm just going to pause the video in case I can't fit it in.